everyone. Welcome to this episode of AM Friday. Today we're going to be taking a closer look at our Metal X metal 3D printing system. And so we're going to walk through the entire process, answer your guys' questions live as we go through it, and hopefully you'll learn a little bit about our metal 3D printing process today.
Yep. So first, a couple of updates from Markforged. We didn't do a broadcast last week, so we have 2 weeks of good stuff. Two exciting things. First, we announced a new office in Dublin, so I actually have the Dublin t-shirt on. This is great for us. We have a bunch of awesome customers in Europe. Previously, we've only kind of supported them through partners and through remote employees. We're going to have a brick and mortar office in Europe, which is a great opportunity to better engage and kind of get a better idea of the European market. So that's super cool. I think there's a few press releases about it, so if you have any further questions, definitely look that up. The other really cool thing is that we announced a partnership with a more in-depth partnership with Siemens, specifically with their CAD software NX, with the end goal of having simulatable parts that basically can be sliced in our software, go to Siemens NX and kind of simulate the actual response of how the part would behave. I think we're starting with metal and kind of going to composites in the future, but it's super exciting. If you've listened to this broadcast before, we talk often about simulating. I think it's maybe our most commonly asked question is, how do you simulate 3D printed parts? So definitely a really exciting development in that respect. It's not out yet, but it will be in the near future.
Yeah, that fits in very nicely with the discussion we had last week and the week before on 3D printing software and how it's starting to get integrated with other tools that these larger enterprise companies are using. So that's really exciting development.
Yeah, so those are two main things. I think there's a bunch of stuff on our website about it. There's some stuff in the news as well. So if you have any other questions about that, definitely look that up. And if you have any questions about the Markforged side, definitely contact us and we can tell you more about it. But with that, I think we're going to kick off just basically a quick kind of quick agenda. We're going to talk very briefly about powder printing versus our type of printing. And then we have a metal printer right over here, and we're just going to go stand over it and kind of talk through the process of the metal printer, the wash, which is our debinding station, and the sinter, which is our sintering furnace. So that's kind of the process of the webinar. But first, I think we're going to talk a little bit about DMLS or SLM versus kind of our technology.
Certainly. So you can really divide metal 3D printing into two generic broad groups, and that's powder-based printing, where you're working directly with the metal powders, and then there's extrusion-based. And so the metal printing under that is binder jetting, and then there's the DMLS type processes, SLM. And so what you get with those powder processes is you get a really high fidelity part typically. We're talking layer heights of down to 30 to 50 microns, yeah. And you're able to hit pretty small features and get fully dense metal parts.
Feature sizes also depend on laser width. So you'll see some machines like Phoenix Systems, who was acquired by 3D Systems, they prioritize making basically a slower printer that prints tiny voxels, where a voxel is kind of a print unit. So they print the super tiny layer heights, and the resolution is insane. There are other printers, like say an Arcam printer, which is not laser based so much as electron beam based, that uses a much broader kind of energy source that is less accurate but prints much faster. So kind of like FDM, where you see kind of different nozzle sizes, different layer heights, that also translates to laser melting and DMLS as well.
Yeah, and so those are some of the advantages. On the negative side of that is you're dealing with metal powders, which are a pretty hazardous material. And so changing materials on a lot of these powder-based machines is kind of a laborious process because you have to take into account a lot more safety concerns when you're dealing with this hazardous material. And a lot of times the cost can be higher because you're paying for a lot more labor because of the materials you're dealing with, and the cost of the machines themselves typically is 5 to even 10 times higher than the system that we offer.
Yeah, so generally when you think about it, there's a few things. A few things kind of go into that higher cost and more intense thing. So one is metal powder is obviously flammable, and as with any kind of microscopic sized powder, is not something you want to put anywhere near your lungs. So you need a lot of PPE, personal protective equipment. You need basically a really effective fire management system. You need a really good ventilation system in and outside the printer. So generally with these machines, you have to construct a room or like a segment of your facility that is specifically optimized for the metal printer. And then the cost of the printer themselves is high in like the $500K to $700K range often. And then to kind of set up that room, to have an employee that kind of manages the machine and works with it, and to actually operate the machine on a regular basis, is another kind of 200-300K. So when we talk about implementing a metal printer, it is often like with these powder bed systems, it's $1 million. It's $1 million thing.
Sorry, my ear thing just messed up.
Oh, okay.
No worries.
I didn't know why everyone was laughing.
Yeah,
honestly.
it's like it kind of like fell out in the middle. It's pretty funny.
All right. But that being said, these printers they've been around for about 20 years, and they're top of the line. Like you can say a lot of good things about these printers. They produce kind of unbelievable quality parts. To get there, though, they kind of take some trial and error, right?
Yeah, and so I think also backtracking a little bit, we didn't really mention like the binder jetting process as much, which is another powder-based process. Instead of using a laser to sinter the parts, you're laying down a fine layer of powder, layer by layer, adhering it together, and then you have a sintering process, post-processing element to that as well. So that's kind of like the powder space. And then there's the extrusion space, which ours falls under. But then there's other machines that are like basically giant welding tips.
Like there's a bunch of specialized machines in the middle space. For the sake of this, we're going to get through this quickly.
Yeah,
we're going to talk about powder. The last point on powder is that it's powder. The powder printers are pretty repeatable, and that once you get a result, you can kind of predict that result will happen over and over again. But to get to when you design a part, there's by no means a correlation to the actual final result, even more so than, say, an FDM printer or an SLS printer or any typical plastic printer that you'd see. The reason is that the metal printing, laser-based printing especially, so binder jetting not quite the same way, but laser-based printing is a super high-energy process. The laser has to be strong enough to heat up metal to a point where it'll either sinter together or melt together. And that process, where you kind of do localized heating, induces a lot of stresses and induces a lot of both geometric and material changes in the part. So you'll see warping, you'll see dimensions not come out quite right. And so when you think about printing a part with DMLS, there's usually some exercise where you're kind of iterating on the actual file and iterating on how you print it and the orientation, how you generate supports and all that stuff. So it's a really industrial process, and once it works, but it's kind of hard to get there. And so that's kind of in a nutshell, that's really what DMLS or SLM printing are. It's just this super high fidelity process that's capable of doing awesome things, but something that really you have to pay a bunch of money for and devote a bunch of energy to.
Yeah, and so then if we look more towards our process, which still works with those same metal powders, but in a completely different way. So rather than having a bed of powder that's being sintered by a laser or having a bed of powder that is being laid layer by layer, we take that same powder and mix it in with a polymer and wax so it can be rolled up into a filament similar to other FDM style printers that you may see that print plastic. And so what this does is it makes it a lot safer to handle. So you can load the materials with your bare hands, switch the materials out, and it also, so along with that safety comes affordability. So printers cost 5 times less than a laser printer because you're not paying for that really expensive laser in that really controlled environment in which you need to sinter metal powder.
Yeah, so basically when we talk about describing metal printing, pretty much every metal printing process or metal additive manufacturing process in one way, shape, or form uses metal powder. There are a few, as Nick said, that literally will like extrude us, like basically use like a weld bead and melt that. But those are kind of niche in the way of metal printing. It's usually metal powders. We are no different. We have the metal powder is there as a part of the process, but you never interact with it because the filament itself is kind of it's a waxy polymer. So in your interactions with with our system are either interacting with a material that feels like a waxy polymer or interacting with a metal part. And so that's kind of the key difference there, is that because the powder is pre-bound, there's no risk of it basically becoming airborne. There's no risk of it catching on fire. There's no risk of that kind of stuff. And that's kind of the kind of main differentiator. And as Nick says, that brings with it a whole number of kind of like cost and time benefits and safety benefits. But the core is still that bound powder.
Yeah, exactly. And so this brings some advantages and disadvantages compared to DMLS processes. No metal process is perfect, so there's trade-offs depending on which method you choose. For example, a laser process is going to render fully dense metal parts that are metal throughout the entire thing. Mm-hmm. Our metal parts have an open cell infill on the inside.
Larger than a certain size.
Right, larger than a certain size. Depending on the size of the part, it will most likely have some sort of open cell infill on the inside, which is advantageous in many situations. But is different from that process, and we can get into that later when we talk about washing. And then in terms of fidelity, the feature size on on Atom, which is what the process that we call our metal printers, cannot get as small as on DMLS machines because sintering with a fine laser is going to be different than extruding from a print head.
Yeah, so with a DMLS machine or an SLM machine, you're constrained in feature size mainly by the size of the powder, which is tiny, and the size of the laser, which is usually a little bit bigger but still pretty small. With ours, you're constrained by basically the nozzle width. And so, and because of that, then the nozzle width inherently, most people here are probably more familiar with FDM than they are with kind of laser-based printing. You know that with an FDM printer, you can only print down to a certain feature size, and this printer is no exception. So it's actually, as a positive, a more intuitive process based on what most people's level of 3D printing knowledge is. But as a downside, is a little bit more limited from the feature perspective than, say, an SLM machine in making small stuff. That being said, it's more reliable as well because the FDM process is kind of easier to understand. It generally produces parts more in the near net shape place than an SLM will the first time, and the parts are kind of more likely to make it through the system successfully first.
Great. So let's see. I think we're ready to show off the printer.
Yeah, so enough of us talking at a desk. I think we're going to go over and show off the printer that's right here. So hold on for 1 second while we kind of walk over there, and we'll get there. Thank you. All right, so we're here on camera. All right, so we lost our audio feedback, but hopefully you can see us. So this is the Metal X. You'll notice it, if you haven't seen it before, it looks like a big FDM, it looks kind of a big version of our other FDM printers with a cabinet on top. So at its core, that's for a reason, and that's because the Metal X as an FDM metal system was developed like or in concert with our composite FDM machines.
Yeah, and so the whole idea is that we've really mastered this FFF printing process, and so transferring that expertise to the metal process allows it to have, it's only a couple features that you really have to tweak to make it so it's a metal process instead of a polymer process.
So on the printing side, the metal printer is actually doing most of the same things that a normal filament printer would do. There's a few adaptations from our printers because the metal, in order to kind of make the metal polymer printable, because it's a little bit trickier to print than say your normal plastic, but otherwise the core process is pretty similar.
Yeah.
So you want to start by walking through the print system?
Yeah, for sure. So you can, I don't know if you can see it printing on the camera very well right now, but
can you drop the camera? Yeah. So open it up. So first thing, the chamber is heated. So the metal printing we use filament. Just like if we open this up very briefly, we can see there's filament here. So this is a metal filament, and then this is a release layer. So two materials at any given point in time. We'll leave it closed because it needs to stay warm. That filament at room temperature is much more brittle than a plastic. So the reason that the chamber is heated is because in order to make the material flexible enough to unspool and basically print adequately, you need to heat the chamber up. It's not, as you said, we opened it, it didn't like burn us or anything. It's like, it's in like the 50, 60 C range, but it is heated up so that the filament becomes more malleable. When it's heated up, that filament starts to behave a lot more just like your typical plastic filament.
Yep, and then as we mentioned, it's extruded and built up layer by layer, similar to other processes you've probably heard of. And as Daniel mentioned, on the right side here is the release material. And so when you print supports in metal, you need a way to get those supports off when it becomes a full metal part. And so the way we do that is by this material that, when put into the sinter, basically disintegrates away under the very high heat so that you can pull the part off of the support.
Yeah, so like our plastic, so if you're familiar with plastic FDM printers, there's either soluble supports or there are basically what we call peel-away supports. And peel-away supports are what we use on our plastic machines. Basically, it's the same material, and you print kind of a zigzag, and then you basically peel it off the metal part because the bonding between the support and the metal part the plastic part is basically less than the bonds between the plastic part itself. With metal, that doesn't work because our sintering process, which we'll get to in a second, basically takes this green or these kind of unbound metal and turns it into a complete part. So if you tried to basically print the metal supports right onto the part, they would fuse onto the part and you'd never get them off. So as Nick says, the way you get around that is basically printing this ceramic material that is a release layer. And in the process, basically, we tack our parts down through the ceramic material to the supports. So it takes a little bit of effort to break them away, but the contacts are very weak, and the support material is doing most of the work in the actual printing process.
Yep, exactly. And so, as Daniel mentioned, the part that comes out of this printer is not your finished metal part. What comes out is what's called a green part, and I think we have an example of one here. Yep. So this is an example of a green part, and this is basically still has that waxy polymer that's in it. So it feels pretty dense, but the surface of it is still pretty soft.
Yeah, so interestingly, these parts, they look like clay. So if you look at them, I don't know how close the camera's seeing, but they're basically this dull gray color. We print with 2 metals we've shipped now and kind of 4 or 5 more on the way. Except for copper, they all look the same, which is kind of this dull gray color because they're defined in color by the kind of rough metal powder and the waxy polymer that's binding them. And you can see here, if you look closely, there's a bit of white in here, right in this edge, and that's the release layer between the part raft and the actual part. So those 2 materials, you're mostly printing with metal, a little bit of support material. And so with this part kind of feels like clay, looks like clay. If we chuck this on the ground, it would break, and we'd be sad. So the part itself here is comprised of a lot of metal, but is not a metal part.
Yep.
And so if you look here, right now the part's actually printing. It's printing the bottom of a raft of a kind of a larger part than this. All of our parts at the base print a raft, which is basically just this kind of lower section here. And that basically allows it to both in the printing process and the sintering process not warp and kind of shrink consistently.
Yep, exactly. So what do we do next after the green part comes out of the printer?
So do you want to stay here or do you want to go to the wash?
I think we'll go to the wash.
All right. So
let me check, make sure we don't have any questions.
Oh yeah. Also.
Oh, it looks like we do have a couple.
All right. So also, by the way, we want to answer as many questions as we can about the Metal X. Be transparent. Talk through your questions, what you want to know, all that kind of good stuff. So feel free to ask questions along the way. We will try our best to answer them. We have a laptop here with the YouTube live stream. So with that, what are the questions we have now?
All right. So the first question is: are the infill percentages adjustable in the same way for the metal filaments?
So right now, the Metal X printer we've been shipping it for 6 or 8 months probably. As you do with any printer, you kind of start by getting one process right, and then you rapidly expand. So with the metal printer, we started with basically one infill setting, one wall setting, which is kind of I think it's pretty similar to our typical plastic one, and we got that pretty close to right. And then in the process now, we'll probably start to add more levers that a customer can turn or crank as they're changing stuff.
Yeah, and depending on the size of the part, as we said, the infill percentage, so a fully dense part is possible for those really.
And I think we actually just released into beta 50 micron printing with a solid infill for small parts. So now there used to be 1, now there's 2. In the future, we'll add basically more variables that you can turn, whether that be like on our plastic printer, the infill density, probably how many shells you can print on the outside of a part, so how thick your kind of outer layer is, and a bunch of other things.
This is a good question. You have just stated that you have mastered the plastic printers. Have you mastered the Metal X? As Daniel just mentioned, this product is still extremely new. To say we have mastered it would, I think, be misleading. We're always making our products better.
Yeah.
And even saying we've mastered plastic, I'd say that's pretty close to true. But we are always making all of our composite and plastic printers, we're constantly improving, adding more materials to, getting better printability of your parts. And so we're always improving the quality. Yeah. So
if I sounded braggadocious, I apologize. I would say this. I was just printing with a PLA printer last night for a personal purpose, and it failed 4 times in a row. And I did not have that happen in a while on our plastic machines. I think our plastic machines have really high reliability. You can tweak settings. You can add fiber, which is typically a hard thing to do. With metal, as we said, we have 1 setting. We've now 2 settings that we're getting really good. And those settings are doing pretty well. And so I think to say we've mastered the system would be completely inaccurate.
Yeah.
We have not. So I would say that it's a process, and we have 10 or 12 really brilliant software engineers who and mechanical engineers as well, who basically spend their time figuring out how to basically make our stuff print better, how to make our stuff sinter better, all that kind of stuff. So we're not, I'd say we take a more Tesla-centric approach where we're continuously improving our product as opposed to kind of releasing it in discrete models.
Yeah, and not to mention more materials coming out. So right now we're shipping H13 tool steel, 17.4 pH stainless steel. On the horizon, we've got titanium coming, Inconel, A2 tool steel.
Copper in the end of the year. So So as we kind of, I think we're good at one thing. We got to be to kind of do anything close to mastery. You have to diversify. I think we've been shipping composite printers for 5 years. To achieve a level of mastery, like they say 10,000 hours. I think with printers it's a lot more. So yeah.
Cool.
Any other questions before we talk wash?
There's a couple more questions. One of them is about the sinter and wash.
Right,
we'll answer that one. How long can green brown parts be stored before sintering? From my knowledge, it's basically indefinite.
Yeah.
They don't have a shelf life.
All right. So let's do this. Let's talk wash and sinter, which are a little easier, it's like shorter to talk about, and then we'll come back to the Metal X and basically answer whatever questions you have here about it.
Perfect.
Sweet. So stepping over, here's the wash. Definitely the most boring part of the process. Also, maybe one of the most important. So what the wash does is it looks like a box. It is a box. It debinds the material. So what is debinding, Nick?
Yeah, so we have this green part that you put in the wash. And as we mentioned, it's got a waxy polymer in it. And so what debinding is it's taking out some of that wax material, that binder material that's inside. Mm-hmm. And so it loses some of its mass through the process, but this isn't the process. As you may have seen our metal parts before, it shrinks, and that comes in the sintering stage. The part doesn't really shrink, and it doesn't really look much different after it comes out of the wash.
It's a little more fragile.
It's a little more fragile, a little more brittle, but it's really, way I like to think about it is it's a preparation for the sintering process.
Yeah, and so what's happening here is we have a solvent in here called Opteon SF79. We can answer questions about that afterwards. It's basically, its job is to dissolve our polymer binder. In practice, it's very safe. Like the concentrations required to actually be harmful by OSHA, who is pretty stringent about this stuff, is I think like 20 times higher than when you could smell it. Mm-hmm. So and this is generally a relatively vapor-free process. So it's not really a security or like a safety concern. But we use that to us. It's fine. To the plastic, it does mean things. It dissolves most of it, and in the process of dissolving, what it's doing basically is as it dissolves tiny channels into the parts. So not channels you can see, but kind of microscopic channels, and those go inside the part and allow the solvent to percolate further. And so that's why when we say open cell infill for parts above a certain size, that's why we talk about it, because wash time is kind of a big thing in terms of how long it takes to actually get the part.
Yeah, and it's directly related to how well that solution can get into the part and wash effectively.
So if you were to print basically a 3-inch by 3-inch by 3-inch solid metal cube, I don't know what the wash time is by this machine, but it would probably be in the terms of months. So, but if you were to print a 3-inch by 3-inch by 3-inch cube that had infill, the wash time might be like 2 or 3 days. So because that open cell infill allows the stuff to allows the material to the solvent to percolate. It basically allows it to go faster. Another way to think about it is this: your maximum thickness of your part or distance from the nearest surface of solid material is exponentially analogous to your wash time. So as you get a further, basically a thicker part, where basically the distance the solvent needs to kind of get into goes up, that elevates the wash time exponentially. So that's why typically MIM parts, because this is a metal injection molding material, are tiny.
Mm-hmm. Yep.
Yeah. Are there any questions about the wash? I'm sure there's a few.
Let's check.
We need to get a big screen in here so we don't have to tote our laptop.
A question about the liquid used for the wash one.
Yeah, so we have information about it on our website. If you have more specific questions, I would say contact our sales team. They're well versed in it. It's called Opteon SF79.
Yep.
Previously known as Opteon Scion, but I think that name changed a year or so ago.
Cool.
Cool. So as we said, not the most exciting part of the process, but an important one nonetheless. So now we're going to talk sinter. So this is, stepping back one more, Nick's in the way of it right now, is the Sinter 1. So the Sinter 1 is our current sintering furnace. Worth noting, we have the Sinter 2, which is coming out sometime in the pretty near future. Yep. But this is, you want to talk through the Sinter 1, the basics of it?
Yeah, so after your part comes out of the wash, it still has some of that polymer. that is encasing the metal powder. And so what the sinter's job is to get rid of all of that and meld those metal powders together to give you that final metal part. And so basically, there's a magical temperature gradient that happens where it rises to a certain temperature, it holds it, and it basically incinerates all of that plastic out and holds it at the perfect temperature to get you that final metal part in the end. And so there's a shrinkage that happens throughout this process. It's about 20% in each dimension, and our software automatically calculates for that. So basically, when you put your STL file into Eiger, which is our slicing software, it scales it up the correct amount, so it prints a little bigger than the part you actually want, and when it comes out of the sinter, it's the size that you want. So there's a couple more details about the sintering process. It happens in an atmosphere. If Daniel, you want to talk a little bit about that?
Yeah. So when we talk about burning stuff out, those little micro pathways that the wash solvent kind of dissolves into the part are critical for the sintering oven, because those are the ways by which the burned away material, which basically becomes gas, exits the part, the remaining polymer. And then as it ramps up, it goes up to 85 roughly % of its melting temperature, and that basically takes that metal powder. Sinter is basically, the term is take a bunch of powder and turn it into its atomic diffusion, basically. Does that, cools the part down and slowly to prevent kind of rapid cooling, and then you're left with your part. In terms of what we sinter with, you sinter in a special atmosphere. It's a mix of what we call inert and mixed gas. These two gases basically combine, and having the high purity of the gas basically at a high temperature prevents impurities from entering the material, and that's what allows you to get high quality materials.
Yeah, so if you're printing in stainless steel, you don't want to introduce impurities while you're sintering the material, because it basically defeats the entire purpose of having a stainless steel part if you can't get an actual nice pure part out of it.
Yeah, and so so we talked about inert and mixed gas. We can get into a little bit more of the operational parts of that maybe in the Q&A section. But in terms of the last thing that's really important is kind of what type of furnace this is. So there's a bunch of types. There's a bunch of furnaces out there. This furnace, the Sinter 1, and its larger cousin, the Sinter 2, are both what we call tube furnaces, which basically means that there is this entire furnace here, which is about 4 feet long, has a tube running through it. You can see it behind Nick right here. The end of the tube is there. The other end, which is the end you actually put parts in, is on the other side. And so that tube is basically has gas circulating through it at any point, and we have basically an active hot zone in the middle, and that is our sintering volume. So the tube is 4 feet long. The sintering volume in this is basically, it's like a 5-inch circle that's 12 inches long, and then the Sinter 2 is, I believe it's a 10-inch circle that's 18 inches long or 16 inches long. So that's how we talk about the furnace itself. And the tube material we use is called is basically it's a non-carbon retort. I believe it's Canthal. And so you talk about impurities. What's the importance of having no carbon in your retort?
I don't know. You should talk about that.
I should talk about it? Fine. Okay. I try to set him up. So as Nick says, impurities are really important. So one way you can get impurities is basically having like impure gas. So if you have like a leaky system, and you allow for example, if you have a leaky system, you allow oxygen into your furnace, your parts would rust because they would oxidize in that high temperature environment. You'd be left with a rusty part. Another thing that you can do is basically when you're heating this up, the entire system gets super hot. So that tube inside, or whatever you kind of line you kind of put nearest to your parts, heats up as well. And anytime you're heating up to that 1200 degrees Celsius range, things kind of start to meld together. So if you have something like carbon in your retort, what's going to happen is as you heat it up, that carbon from the retort, which is kind of, as I said, the retort is the area right around the part, will get into your parts. And so for things like steel, basically like a stainless steel, what part of the stipulation is you have low carbon. So if you have a carbon retort, and you basically are kind of introducing a carbon environment to your steel, and what will happen is the steel will rust more easily. It won't be as stainless as you hoped.
And especially when you're dealing with these low carbon steels that are more weldable, like 316L, this is extremely important when you're trying to maintain an extremely low level of carbon in your material.
Yep. And then the other thing about that is that when you have when you have this carbon in the retort, the impurities for a material like titanium, which is kind of a higher performance material that is more difficult to sinter, are even more severe. So something like with a carbon retort, it's not even necessarily possible to sinter something like titanium. So because we have this carbon-free retort, this area around the part that does not introduce any impurities, the capabilities of both this furnace and the larger furnace will be greater than you would expect. And I think our CEO, who's a brilliant guy, engineer, who talks about it basically as there's a few types of furnaces. There's carbon furnaces, which are you kind of using for lower grade stuff, and then there's carbon-free furnaces, which are typically like super expensive. And we've basically taken the carbon-free furnace technology, the carbon-free retort furnace technology, and brought it down to a price range where it becomes reasonable with this whole system. Yeah, great. So that's a bit of furnace ease, I guess. But if you have any more questions about it, we can do our best to answer them. But yeah, so I think that's
look at questions.
Kind of the gist of it. There's a bunch of details about the stuff that we haven't necessarily said that we're happy to answer, but it's kind of easier to just get through it as people ask.
All right, so should we walk back over to the printer?
It's kind of the coolest. It's the coolest thing to stand next to when we answer questions, right?
All right, so let's see. Can the user print a part, then install a specific part, then continue printing? So I'm assuming here you mean inserting parts, like inserting hardware mid-print. So with our composite printers, this is something that's possible and encouraged in specific instances. We have many customers who do this to optimize their assembly process. In metal printing, what basically puts a wrench in that is the sintering process. So not only is your part going to get up to 12 or 1300 degrees Celsius, it's also going to be shrinking. So embedding hardware during the metal printing process is something that we definitely would not recommend.
Yeah, I was just thinking through that. Like, I wonder if you embedded. Like, so we've had previous things where you embedded a second composite part in the first composite part, and thinking through if that would work for metal. I'd say right now the answer is absolutely no. If it has potential to work, maybe, but it probably is not as advantageous. The reason you do that in composite is because the composite is very anisotropic, in that it has maybe fiber reinforcement in one dimension and not the others. A metal is not like that at all because it sinters all together. It becomes one part, and so geometrically, because it has that infill, it is anisotropic. But in a material way, it is isotropic. So you expect the same properties pulling on a section of material printed vertically as you would printed horizontally.
Yep. All right, so one question. With the ceramic release layer, can we print assemblies and still be able to get them apart after sintering?
Depends on the assembly.
I'm not sure what that question is asking.
I think it's like print-in-place assembly, sinter the assembly, becomes free.
Oh.
I don't know. I've never done it myself. I think maybe, in theory it might be possible, but like, I wouldn't, generally my thought is like, unless you're doing something very small, I'd rather just like print the portions of the assembly and use like, if let's say I'm printing a hinge, instead of printing a hinge that's like print in place, I'd rather print the two parts of a hinge and then just get a pin for $1 off McMaster and push it in.
I assume, I'm making an assumption, but I assume you might be talking about like printing metal jewelry or something, because that's a question that comes up a lot with that. But yeah, it's possible. It just really, it depends on the application that you're doing, if it is the best idea for your assembly process.
Yeah, I mean, there's definitely some niche applications where that could work, but I've never seen it work specifically for our stuff.
Okay, so one question: why aluminum is removed from beta? So, 3D printing aluminum. Should we talk 3D printing aluminum?
I have a long spiel.
I have a long spiel on this as well.
All right, can I do a short spiel and you do a long spiel?
Sure, that sounds good.
So I'll talk the SLM side. So if you notice on SLM or DMLS, very few companies print with aluminum. I think Stratasys actually just announced, when they announced their printer, they said it was going to print with aluminum. I don't know much about the process, but that'd be great for them. The reason that aluminum is so difficult to print, there's like 3 or 4. On the laser side, basically, and this kind of shares with our kind of the sintering side as well, aluminum is kind of readily forms an oxidation layer when it gets to high temperatures, and an oxidation layer is kind of the death knell for printing. So on the and also aluminum particles, aluminum powder can be very variable in size, and its kind of range of melting temperatures for lasers or for like laser-based process is very low. So basically, what they find when most people print aluminum, especially something like 6061, which is kind of your standard wrought aluminum, is that they can't get a pretty part out of it. So there are aluminums that are printed today. Most of them are in the 4000 series. So 4047 is one that you see printed pretty commonly, and that's a casting grade aluminum. So it's a little bit more ductile. It's not quite as strong. But there's a number of reasons why aluminum is hard to print, and there's tons of literature about why it's difficult. There's really few companies out there that do it.
Yeah, and so there's a second part of this where aluminum is hard to print, first off, but the question comes down to, why do you want to print aluminum? And so there are a couple instances where if it was easier to print aluminum, it would make sense to 3D print aluminum. Except, for example, its conductive properties are really advantageous. But a lot of times when I talk to people, the reason they want to 3D print aluminum is because aluminum is what they're used to working with. You machine aluminum all the time. And so what you can actually do is, and it's very lightweight and it's a really easy to work with material, that's true. But if you 3D print in stainless steel and use open cell infill like you have with us, you're getting strength that's higher than aluminum and you're getting weight that's similar. And so getting metallic parts that are load bearing through a 3D printing process, it actually makes more sense in a lot of instances to just 3D print stainless steel and use that as a metal part. And in terms of replacing aluminum, we can talk all day about our composite printers as well, but we won't get into that because we're talking metal.
We're talking metal today.
But so yeah, there's a lot of facets to this. Basically, it's really hard to print, and a lot of times printing out of a different metal can even make more sense than printing out of aluminum, except for a couple instances.
So for reference, aluminum is like maybe in the 300 to 400 megapascals for stress, tensile stress, and a like 17.4 stainless steel is like 1200.
Yeah.
So we print with an open cell infill. So the density is like it's about 3 times density as well. So the strength to weight ratio for aluminum and steel is not dissimilar. And because we're printing with that open cell infill, there's just less weight there. And as we've talked about in kind of some more education-centric stuff, if you go look in our site, generally the most important areas of a part are the edges, the kind of the outside surfaces in terms of loading. So because we print those shells, the strength is near equal. And as we kind of get more advanced and we kind of can print with more shells, then your parts get higher fidelity as well.
Yep. All right, let's see. Is the raft made automatically in the software, or is that user-defined? So the raft is automatically created by Eiger, and you can also toggle to print without the raft if you're printing a smaller part and you want to save some time.
Yeah, so the raft serves a couple really useful purposes. First, as we said, printing helps with, we print with these really cool, we haven't really talked too much about our bed. Our bed is also heated, and we print with basically these removable print sheets. And so when the print ends, it's actually a really cool process where you basically just turn off the suction area of the print bed, take this sheet off that is disposable and costs like $2, and then just peel the part right off. And it's a much like one of the hardest parts of our plastic process is removing parts from the bed, and that just doesn't. It's super easy with metal. So that's one part about it. And then the other side is when your part shrinks, the part shrinks uniformly. If the part was in a vacuum, in a weightless vacuum, it would shrink uniformly. But because you're setting a part on a plate, as it shrinks, there's forces in the system. And so we still can get the part to shrink uniformly, but part of that is using something like a raft, which allows kind of the shrink, if you do the physics of it, the shrinking forces to be uniform around the center of the part. So, and that's a really important aspect. We auto-generate the raft, as we said, so that basically helps that a ton, and that's kind of a great part of the process.
Yeah, so next question is, are these new settings available through software firmware updates, or would we need to purchase a new printer to get those updates? So the great thing about our software is that it's cloud-based. And so what that means is, number one, you can access the software from any computer on Earth that has access to the internet. And number two, that means that your printer can receive updates whenever we push them. And so that's super valuable because you don't have to remember to update your printer. You don't have to buy new software or hardware most of the time to update your printer unless it's an important hardware update. And they're free. So software firmware updates are something that just happen automatically, and that's really thanks to our cloud-based software.
Yeah, and our software team does a great job. We're taking a ton of steps this year to kind of take our software and make it even more scalable in the cloud sense. Because I know some people are like, don't like having their information in the cloud. We say usually our stuff's secure. We're kind of going to a step further with that now in the near future. On the hardware side, I would say two things, just adding on to that. One, the hardware is probably much closer to being like done, locked than the software. Generally, it's like printing is like a relatively simple hardware problem compared to the software. So when we talk about updates, so the printer is closer to being done. That being said, there might be changes internally that we make that say, okay, we want to improve print quality, we change X, Y, Z. We will basically every person, in part of purchasing this printer, there's a success plan that comes with it. And so if we push updates to the system, we will make sure that everyone who has a printer gets sent those updates as a part of the success plan, and basically with install instructions with assistance. So you're not going to get left, basically, as we said, kind of with the Tesla model, you don't get left behind when you buy a printer. You're not frozen in time there. It's a dynamic relationship between us and the people who buy it.
Yeah, exactly. And it's part of that realization of this is new technology, and so we're growing the technology with our customers to help it be the best it can be.
Absolutely.
All right, cool.
We got a lot.
We got a lot of questions. Can this process be used for aerospace parts?
Yes. I mean, so the long answer with aerospace is you have to get aerospace parts approved by a number of regulatory boards, and I think since this is a new technology, it hasn't been 100% approved. On the short, there's no reason why it will not be. I think one big step to that is kind of taking that level of simulation and going forward with that. So the stuff we're doing with NX, definitely would recommend you read into that. Part of that is basically we're creating a better relationship between Eiger, our software, and something like NX, a CAD software, where you, instead of just basically CADing something in something like NX, exporting it as an STL, and then just kind of uploading to Eiger and having no kind of backwards relationship, they'll be compatible between the two, and you can do basically topology optimization in NX. You can then port back the geometry that we're actually printing from Eiger and test on that. I know that one of our application engineers made a really cool generatively designed bracket that basically use this as kind of the launch part for this. Super cool process. I think that'll be a big step in the aerospace side, but there's no material reasons why we shouldn't be able to. It's more probably that the getting parts approved is a long process for aerospace.
Yeah, and that's true for all 3D printing, essentially.
Almost anything.
Yep. One question. Did I understand that the wash time is in days? So that was referring directly to Daniel's statement that if you were to print a cube that's like 3 inches in each direction, the wash time could be a couple of days. It really depends on the geometry and size of your part. I've printed parts that have a wash time of on the order of 10 hours. It depends how big the part is and what that ratio of surface area to volume is. And so it really depends. It can be from hours to a couple days.
Yeah, I've seen parts that take a few days to wash, but they're usually enormous parts.
Large parts.
The typical parts are less than a day. That gripper that Nick just showed earlier, I think that wash time, I just checked, I was just printing that part, and I think that wash time is like 12 to 15 hours. So it's just a kind of an overnight thing. The sintering of it, so just in terms of talking about time, the Metal X prints similar speed to the composites, maybe a little bit slower. The wash takes that variable amount of time in a part size, and the sintering of it takes 25 hours just about, regardless of part size. And also, the washing and the sintering are both batch-based processes. With the wash, you can actually insert and remove parts at any point from the system, so you can parallelize parts. So if you have parts that take longer to wash, you can also it's not like you need to leave them in the whole time, leave that batch in the whole time and not touch it. You can basically, we just have a basket you can really easily remove. You don't have to seal it up and kind of rely on our technology. You can just wash it according to the cloud-based recommendations we give, and also just go with that. On the sinter is a batch. You seal it up and go, but you can basically sinter as many parts as you can fit on the setter plate. So you're not constrained to sintering one part per run.
Yeah, and depending on the size of the parts you're printing, you could be pushing batches through the wash and sinter like 10 parts at a time or even more.
Yeah.
All right, let's see. Does the wash process create hazardous waste?
Hazardous waste. Define. Let's see. Okay, let's see it. So you do, as part of the wash process, you do some Opteon sign evaporates. I don't think that you can drain the system, and in that way you just handle like you would handle any like chemical waste system. So in that case, to some degree, yes. But generally, what happens with the Opteon sign is that it evaporates as you use it, and then you refill the system.
Basically, more specifically, the reason you replace Opteon Scion is because it gets saturated with that waxy material. And so over time, you replace it. And so in terms of safety with the sinter and the wash, you use ventilation for both of them. And basically, this ventilation system is designed so that you can put these machines basically anywhere you want them, whether it's your machine shop, if it's easier to put it in an office space, in your lab, whatever. And so wherever you can stick ventilation in the wall, and then so the process is completely safe. You're not getting any like gases that are run off into your working space.
Yeah. Any other questions?
Let's see. Max temperature. I'm assuming that's talking about sinter. We mentioned that.
Did we say the temp?
Yeah, it gets up to about 1300 Celsius.
Yeah, I think it's like 1250, 1300. It's on our data sheet. I believe it says 1300, and I believe that's correct.
Is the shrinkage rate adjustable?
Calibration modes. The shrinkage rate is not adjustable. So it's funny, we say two numbers about shrinkage. It's because of how, unfortunately, percentage math works. So the part shrinks 17% just about when you sinter it. To account for that, you scale a part up 20%. Those are we had a funny argument in the office a couple years ago about this, about scaling, and the numbers should be the same. Looks like our light just went off. So that scaling is just a factor of basically the percentage of metal inside the filament, and so how much it shrinks is directly relative to the cube root of the percentage of material, percentage of metal powder. So it's not something you ever need to worry about. Our goal with the process is that you never really need to think about scaling up or scaling down your parts. We'll do it for you, and you can just like worry about CADing and fabricating your parts.
Yep. Question about, it just says porosity, question mark.
Take that, you should take that one.
All right, so if you should check out our data sheets that we have online. Our parts are nearly fully dense, so we get tensile strengths and tensile strengths that are about 98%, I'd say, across all our metals of a wrought material. And so wrought is like as strong as you can get a metal with absolutely zero porosity. And so we're hitting just about 96 to 99% of that, depending on the metal. And so while there is a small amount of porosity introduced by the printing process, because it's an FDM style process, we're almost exactly on par with wrought metal.
Yeah, worth noting on those, when we do the when we do those tensile tests, we're evaluating them. We'll do basically us as sintered test versus them wrought, and then we'll heat treat both of them to kind of put them in basically what we would assume to be the same metal state, and then test them. And so heat treated versus heat treated, they're almost on par. And so that's what basically tells you that the porosity of the material, the structure of the material is nearly perfect. But there's a second side to this coin, which is when we talk about the porosity question, well, the quoted porosity is like 95, 96%, I think in that range for most of our materials. But when we talk about porosity, it's a bit more complex of a question, because if you're taking the porosity of an actual part with open cell infill, there's no way you can say it's 95% dense.
Correct.
A part that's solidly printed will be that, but the actual porosity of an open cell infill part is actually related to two things. One, it's basically the ratio between the surface area and the inner volume of the part. Because the inner volume of the part is it's printed kind of in the 30s in density. I believe it's like 37% metal, 63% air or something like that inside the part. And so, the shell is 100% metal. So basically, if I have a part that's super thin, that's basically almost all shells and no infill, then the part is almost fully dense. If I have a cube, which is mostly kind of the internal infill and not much shell, then the actual porosity of the part is different. So when you're talking about porosity on this process, it's a little bit murkier of a question relative to kind of what you're expecting. In terms of where we're trying to print metal, basically when we talk about the 90-something%, that's basically porosity relative to where we're trying to print something that's not porous. But the process intentionally has porosity in it.
Great. Total time floor to floor for the binder removal and sintering. We talked about times.
Yeah, depends on, as we said, depends on the part. Sintering is a little more in the day. Debinding can take a variety of times.
All right. What is a 2.9% hydrogen needed for?
I believe so this is someone who's read our actual gas sheets. The 2.9% hydrogen is part of the mixed gas. The point is nitrogen. I'm a mechanical engineer. I'm not a material scientist, and I would not be able to answer that question as well. If you have a reason for asking the question, feel free to reach out to us, and we can maybe get you a more detailed answer. But I don't actually know.
Cool. Powder volume percentage. I don't think that's something that we can share with you.
I don't think we share it.
Accuracy of size. So I'm assuming. So this is talking about post-sintered part, accuracy of size of your print compared to your design intent. So what we officially say is near net shape, and so what that basically means is again, as we always say, it's geometry and size dependent. And so what I can say is that our printer can print down to about 50 micron layer height, which we're just introducing. Typically, it's post-sintered 125 micron layer height is another setting you can do, and so. In terms of, it's usually in terms of printing, it's about on par with what our plastic and composite printing is, which in the XY you're seeing accuracy down to a few thou, and then the sintering introduces a little more inaccuracy to the system, depending on the size of the part as you introduce shrinkage. And so one fix to this, depending on the geometry of the part, is if you're looking for a super high precision finish on a part, post machining is something that you can do with certain geometries.
So the plastics, as we say, it's like going back to my earlier mastery comment. We know a lot more about our plastics. We've done a lot more stuff in terms of them, and we can have a bit more of a confident tone when we talk about accuracy. On the metal, I think our formal company line is near net shape. The reason we say that is because we don't want to overpromise. We like to underpromise, overdeliver. And as Nick says, if you need super precise parts, you can post machine them. You just stick them in a mill. It is just metal. You can remove as much as you need. You can post machine. You can polish. You can sand. You can heat treat. You can do any of that stuff, which I think ties into the next question, which was, can the sinter 1 or 2 be used to anneal 17.4 to H900? Right now, no. So I should say, from a capabilities perspective, yes. Is it capable of doing that? Yes. Do we offer it as a feature right now? No. There's a few reasons. One, as we say, trying to get the few things really well done before expanding. And two is kind of figuring out what the actual customers need. So for this, because it's a kind of a controlled atmosphere furnace, heat treating does not need a controlled atmosphere furnace. You can stick it in any furnace. So H900s, you heat it up to 900 degrees and then you cool it down. And so if our target customers already have furnaces, it's probably a faster and more efficient and cheaper process to just heat treat in your own furnace.
Yeah.
That being said, the Sinter 2 will have significantly more bells and whistles than the Sinter 1. And so there's a chance that something like that comes available in time because it is technically feasible. But right now, no. And as far as I'm aware, there's no formal plan to do something like that.
But in terms of heat treating your metal parts, these parts can be heat treated just like any other metal part.
Yep.
And so that's something that you can do. It just does, at this point in time, doesn't make sense to use your Sinter 1 bandwidth to do that process.
Yep. And then the other thing is we have in our design guides, we have both stated kind of heat treat standards. As you say, H900 or H1150 are two common ones for 17.4. H13 doesn't really have a name for it, but it's like an air quenching process where you heat it up to like 560 Celsius, I think, or 590 Celsius, and then air quench it. We have all that detail in our in both the data sheets and the design guides. Data sheets kind of show the quoted properties when you do it, and the design guides show kind of describe the process. As Nick says, it's just like normal metal, but we do like to kind of centralize the source as possible.
Yep. Do you have software for planning sintering runs? How can you plan on taking account enlargement and rust? We talked about the second part already. Software for planning sintering runs. So all of our machines are integrated with Eiger, and so as we mentioned, sintering runs are batch-based. So you run a batch that lasts a bit longer than a day, and then that's standardized for no matter how many parts you're putting in or whatever the part is. It's a standardized sintering profile.
So yeah, all machines Wi-Fi connected. It makes life easy. So you can see your printers, your washes, and your sintering furnaces, what is in them at any given point in time. And then for the sintering furnaces, you can see all the details about what they're running, how well they're running, if they failed, if they've had any issues.
Yeah. All right, what range of metals have you printed and sintered? We kind of mentioned this. Right now, you can buy 17.4 pH stainless steel and H13 tool steel. On the horizon is A2 tool steel, Inconel, titanium, copper. Am I missing any?
A2, Inconel, D2.
D2 as well.
Yeah, if you've ever, we have a cool little demo that we bring to trade shows that is impellers. We've printed all those materials. I'd say copper is kind of a newer addition to the we've printed list. But the old demo that we've had for a while and we've been capable of printing is the two we've shipped, 316L, A2, D2,
316L as well,
and Inconel titanium.
Yeah.
So those ones are the ones that we've eminently planned and we are printing. It's just a matter of we don't ship materials until we know we can do it really well. So again, start with doing a few things really well, expand out, and do more things well as you can.
Compliance and conformity, electrical and emissions for printing, furnace, washer, and materials compliance. Really general question.
Lots of broad question. On the data sheet is the best answer. Or if you have specific questions about whether something conforms to a standard that you have, please reach out to our sales team. There's if you go to our website, there's a get a quote on the Metal X. They can give you much more than a quote if you're interested on that kind of stuff. There's also contact us. If you have a specific question, you can leave it there and we can answer it. I know that the power details are, the wash is basically the wash is pretty similar to the printer in that it plugs into the wall. You rather have a 20 amp circuit for it. And then the sinter is a little special. It has like a 200 to 240 volt connection. It needs a little bit more work. I would say that when we part of buying the printer is that we help you install it, or one of our partners helps you install it. So So we're not just going to ship you something and then act like you have the expertise to actually put it all together or pretend that that's the case. So we want to make sure that when you buy a system, we will help you install it and get you up and running on it, and make sure that all your facilities are ready to go.
Yeah, and that fits into the next question, which installation tips. As we said, we sell it with a success plan, so you get help with your installation and troubleshooting throughout the whole process.
Yep, and all of our partners, or the partners that work with the Metal X, are all trained to install it as well. So most of our partners actually have Metal X's in their facilities. They print with them every day as well. So the expertise on the system does not stay in this building. It does go out further, and they know how to do it. They know how to kind of install and maintenance the machines as well. To say that like us as like a relatively small but growing company could maintenance a big fleet of printers, I don't think we could do it. So we rely a lot on our partners who do a fabulous job with that.
Yeah. Biocompatibility, no, our metal parts are not biocompatible.
At this point in time? Again, that's like a certification thing. So a certification and kind of investigation thing, we've not investigated it yet.
Yeah. What will be the minimum wall thickness size?
Minimum wall thickness. I don't honestly. It's dependent on nozzle diameter. And the nozzle diameter is variable. So I think our newest nozzle is 250 micron. So theoretically that, but it really depends on. It will depend. It may well change in the future. It may well get upgraded, but that's probably in the area. If you're looking to print super small, precise parts that have like really thin features, the Metal X may not be the right fit. But the best way to kind of figure that out is just if you have an STL, if you have a CAD file, get in contact with us and send us the CAD file, and we can kind of look at it and tell you if we think it's going to be good or not.
Yep. Is this video available for the webinar for review? Yes, this will be on YouTube after the live cast is done.
Yep.
One question, 3D printing question mark. Yes.
Yes.
When is Center 2 going to be available?
I don't know if we have a quoted time.
Yeah.
Pretty soon.
Yeah.
Pretty soon. Without it, very confidently this year.
Yeah.
But most likely sooner.
Do I need to change the nozzle when changing the filament? Is it one print head for all? Yeah, or no, you do not have to change the nozzle between filaments. The print head, the hardware just stays the same no matter what.
We do have a guide for material changeover. Yep. There's some things like you want to change out. We have wire brushes the nozzle wipes itself on.
Yeah.
You want to change those kind of regularly. That's one of the big advantages of our process is like changing materials is a lot more like changing materials in a plastic printer than changing materials in a powder printer.
Exactly.
Where like basically you're changing the filament and make sure none of that old filament is there, is anywhere that's going to contaminate it.
Has anyone ever tested using the 3D printer in fixture creation for CNC milling and turning?
In metal, interesting. I don't know if they've ever, like, in terms of soft draws, I don't know if I've ever seen a metal printed soft draw. We see that for our composite printers literally all the time. I don't want to, we're talking metal today, but definitely take a look if you're looking at that.
Yeah.
For milling and turning, I don't know if like, those type of fixtures are generally bigger. And they're kind of bigger and blockier and sometimes don't need to be as strong, so it might not be the best fit. But we see tools and fixtures working on the metal side is more in like the more tooling side of it. So like jaws or like grippers that need to be like handling a lot of parts, something that's a high wear component, potentially some types of molds, brazing fixtures, stamping, metal forming, that kind of stuff is the tools and fixtures that's a lot easier to kind of justify using the Metal X for.
Yeah. Can you weld metal parts?
Somebody
yes.
answered it.
Look, there we go.
Thank you, Zachary.
Zachary, hello, fellow customer. And once 316L comes out, which is a much more weldable steel, that's going to be something that we'll see a lot of customers.
17.4 is for all of its merits, not the most weldable.
Yeah.
It's possible, distinctly possible, but not the best.
Yeah. Thank you, Zachary, for chiming in. How does 3D printed metal react to being used as a punch and or a die in a press brake? Can you make sheet metal parts and bend them without cracking? So to answer the second part of your question first, I would not recommend 3D printing sheet metal parts. That it would make a lot more sense to fabricate those in more traditional ways. But making the tooling to form sheet metal parts is something that customers do and you can do as well. It's really helpful for prototyping those stamps or doing short runs of those stamps as well, or even production runs. And so it allows you to iterate the geometry of that part really quickly and so that you can make tooling a lot faster.
The lights just turn off again.
Let's see. Does an owner of Metal X get support with Eiger during the design process?
So what is it?
So we have a support team that helps people with Eiger all the time. So it's not necessarily like they'll walk you through designing your part, because that's something that you'll do in whatever CAD software you prefer. But in terms of using Eiger as the slicing and management software for your prints, questions on that are answered by our support team all the time.
And we have a design guide. We're working on we have a new part of our website that's markforged.com/learn. There's a learning library. There's some portion to designing for metal now that we're working on building out. Are there any more questions? It looks like we're about to get the hook.
Yeah, we've got 2 more questions, looks like.
All right, so we'll buzz through these 2, and then if you have any other ones, we'll try to respond to them after the fact. But thank you so much for asking all these questions.
So a question about clogging. So that's the reason that we closed this immediately after we opened it. So the printer's really good about not clogging. There's a bunch of fail-safes for that. Number 1 is the brushes that are in the back left of the printer that the nozzle wipes on to make sure it doesn't clog. And also keeping the chamber heated at a constant temperature also helps reduce clogging. And so, we have a lot of
Sinter also has filtering. If you're talking about the clogging for the sintering in the wash, it's all I would say 2 things: lots of fail-safes and generally pretty reliable systems.
All right, I think that's all of our questions.
All right, so thanks. It was, an hour and 3 minutes. So we spent a while doing this. There's probably many more questions about metal. I think in the near future, we're going to dive deeper into individual parts of the metal system. So if you enjoyed this, definitely come back next week. I don't know do we know what we're talking about next week? We're talking about costs,
Yeah.
Costs. We just talked a little bit about kind of operating costs and kind of a broad context today. We're going to dive a little bit deeper into what the actual ROI of using a machine like this is, the realistic costs of how much you can expect to spend, and that kind of stuff. Definitely come back. It'll be on our YouTube channel. We'll send out an email about it as well. And if you like this or have feedback, feel free to send it in as well. And with that, thanks so much for your time and happy printing.
Yeah, thanks guys.